Hello, it's me, V. Anton Sproul, with another discussion of how you can learn to think like a programmer. This episode is going to be a little different. I received a suggestion from a viewer, Jesus Castello, and let me apologize in advance if I'm mispronouncing that. He asked me to solve a particular problem from HackerRank.com, a programming contest site, and explain the steps I took to reach the solution. I looked at the problem, and it's a good one to discuss, so here's what I'm going to do. I'm going to walk through the steps I took to reach a solution, but along the way, I'm going to offer ideas that occurred to me that one might use to reach a different solution to the same problem. I'm not going to show my actual code until the very end, so at any stage in this discussion, feel free to go and try it on your own, or maybe even try it different ways. So here's the problem. It's called matrix tracing. The idea is that you can write a word as an m by n matrix of letters. The original problem description gives this as the example. The letters of the word mathematics are placed in this matrix in a special way such that starting at the upper left letter and always moving either to the right or down, when you reach the bottom right letter, you will have traced the word mathematics. Now, what the program has to do is, given those numbers m and n, that is the width and height of a letter matrix, figure out how many different ways there are to get from the upper left to the lower right. Now, I should say that the original problem description makes this into a batch processing program with specific requirements for input, output, what to do if the result is very large, and so on. So the first simplification I'm making to this problem is to ignore all of that and just worry about handling one set of input. If I can get that to work correctly for any input, then the rest of it should just be boilerplate. So the first thing to realize is that the fact that the matrix spells out a particular word isn't necessarily relevant to the solution. That's the kind of red herring that's often thrown into these programming problems. All you need to worry about is how many ways there are of getting from one corner of a matrix to the other, just moving to the right or down. That means there isn't necessarily a matrix involved in the solution of the problem. In other words, we might imagine two variables, row and column, that keep track of where we are in a particular matrix. And the question is, if we always have a choice of incrementing one or the other, how many sequences of increments are there that result in getting to that particular place? My first thought was to make a table of answers for a few sample problems and see if there was some sort of pattern I could discern. This is an approach I talk about in my book. In this case, I put the numbers into a spreadsheet. If you've seen my last video, you know that I think spreadsheets can be a great tool for problem solving. The hope was that I could see a clear pattern in the progression of numbers, and then maybe find that the answer is a direct formula. Now, looking at these numbers, I'm pretty confident that there is a pattern to all of this, but I'm also pretty confident that I don't yet know what it is. Now, having actually solved the problem in a different way, I can come back now and see exactly what the pattern is. So if you do see the pattern, this is a great way to find a solution. It does take a little work at the beginning to manually go through the sample cases and fill in the chart. And sometimes that's hard for developing programmers because that may feel like you're not really making progress because you're not actually programming yet. But if spending some time with a piece of paper helps us find a solution, that may actually be a faster way to the goal. But at this point, especially without all the numbers in the chart filled in, I didn't know what the pattern was. Also, it occurred to me that I didn't really want to solve the problem this way. See, doing it like this, it's really just a math problem. It's not so much a programming problem. There's nothing wrong with that, but I wanted to solve it like a programming problem. So then I had another thought. In these videos, I don't know that I've talked yet about finding analogies. This is the main way that experienced programmers put their experience to use in the problem-solving area. Sometimes there's a hidden analogy between a problem you've already done and the problem you're currently working on. By analogy, I mean it's not the same problem or a direct variation on the same problem, but there is some sort of connection in the underlying problems that lets you see how the first solution may be related to the current solution. In this case, believe it or not, I thought about mazes. There's lots of fun programming exercises dealing with mazes made out of arrays. So for example, you might have an array of characters where an asterisk means there's a wall and a space means there's no wall, and the goal is to get from one particular location in the array to another particular location. One way to solve that problem uses recursion. If you haven't studied recursion yet, I have another video already up on recursive problem solving, and that includes a link to that chapter in my book. So if you want to try this approach to this problem, you might want to go back and check out that video too. Anyway, in this case, the recursive solution goes like this. Beginning at the start position, you make a recursive call in every direction where there is no wall, in essence asking, is there a way to the exit from there? And with this method, it's easy to change it to count the number of solutions to the maze if there are more than one, by changing the question to, how many ways are there to the exit from there? I'm leaving out a lot of the details, but that's the basic idea. So when I looked at this matrix and this problem, I thought about a series of rooms with like fire exit doors between them so that you could only go through them one way. Then I could apply the maze technique that I already knew. So that's what I did, and the code I'm going to show at the end of this video uses that idea. Start at the upper left corner, and then make recursive calls in both directions, asking, how many paths are there to the lower right corner from where you are? However, after I got that to work, I realized there's a better way to conceptualize the recursion. Instead of thinking of keeping inside the same matrix for every recursive call and just changing the position within that matrix, I can think of each move to the right or down as reducing the size of the matrix. In other words, if I start in the upper left of a 4x3 matrix, I could think of moving one column to the right or one row down in that same matrix. Or I could consider that because there's no way to go up or left, no way to go back, moving either way reduces the problem, either to a 4-column 2-row matrix or a 3-row 3-column matrix. Now you might think, well, doesn't that just work out the same as the original recursive conception? Well, it does mathematically, but it does result in a somewhat different implementation, as I'll discuss when I show that code. So anyway, that's approach number 2. Having solved the problem using recursion, I then wondered if there was a reasonably direct way of doing it without recursion. Of course, there's always a possibility of solving a recursive problem without recursion, but sometimes that means doing what I would call iterative recursion, something you see a lot in search problems. Because recursion effectively uses the system stack to create a trail of breadcrumbs, or for you Brady Bunch fans, a trail of popcorn, a way of keeping track of all the numbers in the previous calls. So sometimes when recursive solutions turn into non-recursive solutions, that uses an explicit stack to keep track of those values in basically the same way. And I wanted to find a non-recursive solution that didn't use a stack or something else that effectively mimicked the recursive solution. That's when I realized that the recursive calls were effectively totaling up the number of paths and wondered if the cells of a matrix defined by those m and n input values could be used instead. At the beginning of this video, I talked about how there's no actual matrix necessarily involved in the solution. It's just something described by the input that we work with conceptually. But I thought, well, what if I stored the number of paths to the lower right corner from each cell in that particular cell? That sounded doable because that number for any particular cell should be equal to the sum of numbers in the cells to the right and below. But for that to work, I knew I couldn't start in the upper left. I would have to start in the lower right and then work backwards from there. I could start with a 1 in the lower right corner, then fill in the bottom row from right to left, and then the next row above that from right to left, and so on. Of course, if a cell doesn't have a neighbor to the bottom or to the right, that has to be accounted for. But I tested the basic idea and it worked. I didn't write a program for it though. I tried it out in a spreadsheet. And here is that spreadsheet test. Each cell is the sum of the cell to the right and the cell below. That's the formula, except for the lower right cell, which is set to 1. And it shows that for a 4x4 matrix, the answer is 20. You might notice that you've kind of already seen this spreadsheet before in a different way. Yeah, that's right. It's a flipped version of the spreadsheet I was working on for approach number 1. So approach number 1 and approach number 3 might result in similar code, and then again, they might not. But you can see how there are a lot of different ways of looking at the same problem. In some cases, they may turn out to be different roads to the same destination, but which road is easiest depends upon the traveler. For different programmers, different approaches will make more or less intuitive sense. And by being willing to look at a problem in several different ways, you can often hit upon an approach that just clicks, and then the rest of the solution is fairly easy. So before I show you my solution, I want to encourage you to try this on your own. Take one of the approaches I've shown and see what you come up with. There are lots of different solutions for this problem, and many of them are going to be cleaner than the one I'm about to show you. If you work out something good, feel free to post the relevant part of your code in the YouTube comments if you want. That's one good thing about the new Google Plus comments, there's no size limit. So here is the code I wrote. I didn't clean this up, it's just what I wrote at the time. It follows approach number 2, the recursive solution. You'll note that the function that does all the work takes 4 parameters to indicate both the size of the matrix and the current position within it. The first 2 parameters are always 1 in the initial call, which is why I have to use a wrapper function, and that's another thing you can read about in that free chapter from my book if you want. What I realized after writing this, though, is that it's possible to just modify the size of the matrix for the recursive calls, what I was showing you earlier, in which case you don't need the positions to be passed at all, because you're always in the upper left corner of whatever matrix you're dealing with. So that's another possible improvement for someone else to try. So that's it. As always, I hope this helps you develop your problem-solving abilities and learn to think like a programmer. Big thanks to Jesus for his suggestion, and if you have any ideas for future videos, feel free to send them my way or post them in the comments. And please do subscribe and/or hit the like button if this video was helpful to you. Thanks.